you very much for the presentation, and thank you very much for the organizers for this invitation. It's a pleasure to be here. My name is Mikel Sanz. I'm from the University of the Basque Country, and the title of my talk today is Digital Analog Quantum Computation. So, have any of you heard about this topic before? Oh, perfect. Only this is good because I have prepared a quite pedagogical presentation, so I think it will be, hopefully after the talk, much more people can raise their hands. So the idea of digital analog computation, quantum computation, is that if you have analog computation is quite resilient against noises. Essentially, the reason is that you don't have to, it does not require too much control on it. But it lacks of flexibility in the sense that you can only simulate what you have, what the system is providing you. The idea of digital analog quantum computation, all in all, is that is to try to improve the flexibility of analog computation, but keeping this robustness, or as much as possible of this robustness, by not increasing too much the control required in the system. So this idea was proposed many years ago when I was a postdoc in the group of Enrique Solano, and afterwards this was developed by Ana Martin, one of my PhD students, that she showed how to introduce, how to use this digital analog quantum computation with quantum algorithms. And now most of the work done in the last years is done by one of my senior PhD students, Mikel García-Dandoin, who is defending this year, and now Alex is jumping into that. And the work that he's doing now is essentially try to see if it's possible to extend this paradigm to qubits. So many of the things that I'm going to show you here today is work of Mikel. So the outlook of my talk is that it's divided as here. So initially, I will try to motivate you why digital problems that are behind digital quantum computation and analog. And I hope that this is a motivation, or this is a motivation for introducing digital analog quantum computation. I will define you how to do this with some examples and some of the latest results that we had, and also analysis with respect to errors and stability. Afterwards, I will tell you how to use this paradigm with the different quantum algorithms, in particular quantum Fourier transform and Harrow-Hassim-Lloyd algorithm, but a little bit about quantum phase estimation and QAOA. And finally, some of the impact that this protocol had, and conclusions and perspectives. So probably all of you know about digital quantum computation, but let me start from scratch just to establish a common language. So a way or a recipe for a quantum algorithm is this kind of quantum circuits. No? Over here you have the qubits, and this is time, and essentially one computation consists of creating a unitary that is acting on the initial state and producing a final state, which is the answer of your computation. Universality theorems tells you that you can decompose this global unitary into single and 2 qubit gates up to an arbitrary precision. And therefore, the ingredients in digital quantum computation are single and 2 qubit gates. But how the single and 2 qubit gates are actually implemented in physical systems? Well, I have chosen superconducting circuits, but this can be extended to other platforms. And I'm probably oversimplifying some parts. I know it for the people here that know about superconducting circuits, but the conclusions behind are correct. So this is a typical shape of a superconducting circuit, where here the squares that you have here are the superconducting circuits themselves. These lines, these outlines, are the control buses of the qubit, and these lines here connecting the qubits are buses that are used for the interaction. This is how really you perform the interaction of the 2 qubit gates here. So essentially, when you want to make or to perform a 2-qubit gate between these 2 qubits, what you have to do, as this is a kind of a cavity, what you have to do is to put in resonance these 2 qubits with respect to the cavity, and then some kind of interactions between the 2 qubit emerges. When you want to stop this gate, what you do is to use the external control lines in order to put one of the qubits of resonance, or both of the qubits of resonance. And then the interaction between these 2 qubits is essentially the overlap integral of this interaction system. This works pretty well when the difference in the frequencies is high. This is exponentially suppressed in general. However, when we want to scale up and you have a lot of qubits which are connected between them, and you want to perform a 2-qubit gate between 2 of these qubits, the problem is that the electronics that all the classical electronics that makes all these things work is working in certain frequency range. And you cannot actually go beyond that, because then you cannot measure, you cannot do anything there. So this means that when you are scaling up in the number of qubits, the frequencies, or the difference of the frequencies between qubits that you can introduce is smaller and smaller. This is called spectral crowding. And this leads to the fact that then the frequencies are not so far away. And when you are doing some kind of interaction or some kind of control in one of the qubits, then this is seen by the other qubits. And this is a kind of a parasitic interaction that you don't want there, and which is called cross resonance. There is another problem, that is what means to perform a quantum gate, no? From a control point of view. This means that if you have, you want to perform this unitary that is defined by this Hamiltonian and lasts for a time t0, and you want to apply it in t0. The idea is that you want to apply this gate, you have to switch on this Hamiltonian infinitely fast, run it for t0, and then switch off infinitely fast. As a physicist, you know that you can do nothing infinitely fast. What you actually do is a kind of pulse shape that you put. I have lost the connection with Zoom. Not good at all. Is it still working? Okay. So you can switch. You have to switch on and off following some pulse shape that is obviously smooth and depends on your electronics. So what you are actually doing is not this unitary, it's this kind of unitaries, which is a Dyson series of a unitary, because it's time dependent. It's a time dependent Hamiltonian. This means that okay. Well, okay. This means that when you have a large quantum system, which is composed of many quantum gates, what you have is on one side switch on and off interactions that you don't that are not exactly the unitaries that you want to perform, and additionally you have this kind of cross resonance between the qubits. You can reduce some of these using quantum control theory, quantum control techniques, that essentially tells you that you have a landscape of control pulses, but you can find an effective one that is global, that reduces these errors. But the bad part of this, or the wrong part of this, is that you have to be able to simulate these in a classical system. But the goal of quantum computation and quantum simulation is to go to a system that you cannot actually simulate in a classical computer. So this is not, you cannot apply it always. Okay, let's go now to analog quantum computation. Analog quantum computation consists of a system, which is the one that you want to simulate because it's physically interesting, high temperature superconductivity, whatever, and a simulator, which is a physical system that you can control, you can measure. Both, they have a very similar dynamics. Could be the same or at least very similar, but it has to be very similar not only in the parameters that you have, not only in the terms that you have to be also similar in the parameters. For instance, a traditional or a historical example is high temperature superconductivity that you have and call atoms. They have very similar, exactly more or less the same Hamiltonian. However, the range of parameters in which you can run the cold atoms is much smaller than the ones that are necessary for the simulation of high temperature superconductivity. And there has been many years of work on this in order to increase or to approach both. The good point of analog quantum simulation is that it allows you to simulate systems of interest. And the other point is that the simulation is extremely robust. The reason is, as I said before, is because analog simulation does not require too much control. So essentially, you are using the dynamics provided by your quantum system and just allow it to work. This means that it's an scalable system. So you can the error when you are scaling the number of qubits is relatively low. What are the drawbacks? The drawbacks, the first one is the lack of flexibility. As I said, you normally have certain dynamics and you have to work with this. And if you want to change a little bit some of the parameters, sometimes it's even impossible. The second one is that this of course limits the applicability. And the second one is that as any analog system, also in classical systems, the error is not controllable. So you cannot ask the system to reduce one half your error. This is not possible. So the idea of digital analog quantum computation is, can we somehow increase the flexibility of analog systems in order to increase the applicability while keeping the robustness that we said before? Well, the idea behind is that we will use the source Hamiltonian that is provided by the quantum platform. So you just use, if you have a spin system, you use the Hamiltonian you have there. If you have trap ions, you use the Hamiltonian you have there. If you have a superconducting qubit, you use this one. And we increase the set of tools, the toolbox, by single qubit rotations. Then we can prove that what you have is you can construct an arbitrary Hamiltonian. This means that this source, essentially any source Hamiltonian plus single qubit rotations is universal. Instead of proving theorems and so on, let me explain you with a very simple example. Let's assume that we have as a source Hamiltonian an all-to-all IC Hamiltonian which is homogeneous. So you have the same coupling for every term. And you have single qubit gates, yes, X gates, that's all. And the goal of the problem is to simulate an arbitrary IC Hamiltonian with arbitrary couplings in front of that. This is our problem, and this is our goal. Okay. Now let's consider just the case of 3 qubits, but it works essentially the same for any number of qubits. What we have is that our source Hamiltonian, we run our source Hamiltonian for T1 and perform X gates in the first and the second qubit. The only thing that we need to know is that if we have unitaries and an exponential, then the unitaries can go to the Hamiltonian, and in the Pauli algebra, x at x is minus z. This means here that you have the first term that's changed twice the sign, so that's nothing. The second one changes 1 due to the Z1, and the second one changes also the sign due to the Z2. Now let's do the same for the first and the third qubit and run it for time T2. Here you have the T2 and changes the first and the third term in the Hamiltonian. And finally, let's do it in the second and the third one. Here, what changes is the first and the second term. If we put all of this together, what we have is that as they commute, the Hamiltonian of this unitary, the unitary that we are doing here, is just T1 minus T2 minus T3 minus T1. So this is a system of equations that you have, and this is the one that you want to create. So the goal Hamiltonian. So if it's possible to find T1, T2, and T3 such that they fulfill these equations, then you can generate it just by solving this system. No? The protocol, in general, consists of applying X gates in all possible pairs of qubits. And what we proved in the original paper is that this is universal. So this matrix, the matrix generated by this way, is always invertible. Or the number of time slides that you have here is quadratic, because it's all possible pairs of qubits, quadratic in the number of qubits, of course. So it's 1/2 n minus 1. So it's quite efficient. The system of equation is not growing, it's not scaling up too badly. And therefore, by this way, you can generate an arbitrary Hamiltonian, two-body Hamiltonian with the couplings that you want. Essentially, what you are doing, if you want, is to start with a fixed coupling for all the qubits and different times, and map it to same time and different couplings. But it looks quite specific, because we are working with a set Hamiltonian. But what we were able to prove Mikel was able to prove in this paper, is that we can extend it, and starting with any two-body Hamiltonian, we can generate any two-body Hamiltonian that we want. This can be done additionally only. The protocol is essentially, instead of applying just pairs of x gate, what we have to apply is all possible combination of x, y, z. So this means that for each of the previous cases, we have nine of them. So you just are increasing in a constant. Before it was 1/2 of n minus 1, and now it's 9 times n 1/2 n minus 1. This additional, of course, in the previous case, everything was commuted. But here, what you can do is also to use Trotter decomposition, and then this 9 times is just increased by nt, the number of Trotter steps that you want to introduce, and therefore you have a controllable error also there. Until now, we were talking about a structure that is essentially slides of analog computation here, sandwiched by single-qubit gates. This is what we call a stepwise digital analog. It's possible to prove that in the noiseless scenario, this is equivalent to digital. And when you have control errors, for instance, switching on and off, this is not an advantage with respect to digital, because essentially you have to switch on the whole analog block and switch it off. So instead of having the number of gates that you have, the error in each of the gates, you have the error in the whole block. So it's very similar. So we came up with an alternative approach, which we call bank digital analog. The idea, imagine that you can perform the single-qubit gate infinitely fast. Then, by the sudden approximation in quantum mechanics, this means that this will mean that if you have the analog, you can have the analog dynamics and perform on top of that the single-qubit gates without performing any kind of error, right? But of course, again, single-qubit gates anything can be performed infinitely fast. So you have some time scale, some delta t. This delta t, what we were able to prove is that the error introduced by performing the single-qubit gates on top of the analog dynamics, so without switching it on and off, is proportional to delta t over g to the third. This to the third using symmetric Trotter decomposition. Essentially, the idea is that if the dynamics associated to the single-qubit gates is much faster than the analog dynamics, then you can do this without making a huge error. This is essentially the idea. We have also studied the effect, because until now everything was perfect. Now we have considered also some kind of errors. On one side, we consider control-associated errors. So for single-qubit, 2 qubits, and analog blocks, we were considering that instead of the right time corresponding to each gate, we have some time which is taken from a Gaussian distribution, Gaussian probability distribution. And it was explained before also in the previous talk. And we were also considering environment-associated noises, so bit flip channels, measurement channels, and amplitude damping channels. This is done. This part of the control is done in this paper, and the whole thing was done in this one that was published last week, actually. We also, afterwards, I will show you the results of the simulations considering these errors. But now let me continue with another kind of errors, which are the characterization errors and stability. Characterization errors are coming from the fact that imagine that you want to, as I said before, using the protocol, you want to construct this problem Hamiltonian, that is a two-body Hamiltonian. And you assume, after measuring your quantum platform, that the Hamiltonian is this one. However, you have not characterized correctly your Hamiltonian, and actually the real dynamics is this one, HS prime. However, for finding what is telling you the digital analog approach is that you have to find the set of times for the analog blocks. And therefore, instead of constructing this Hamiltonian, that is the one that you wanted because you thought that this was your right Hamiltonian, you are constructing another, HP prime. The question of this stability is how far the dynamics produce, so HP prime is from HP. Because if just a small error in the characterization means that this is exponentially far away from the target one, then this construction is completely useful because in realistic scenarios, you can never, ever characterize perfectly a Hamiltonian or the interaction Hamiltonian you have in the system. So in order to measure this is still unpublished. This is in a paper that we hope to put in arXiv next week. We defined weak stability in the following way. So imagine that the state that you are producing, that you want to produce with the real or the desired Hamiltonian HP is rho. But the one that you are producing, which HP prime, is rho prime. So we say that and you want to, afterwards, you want to measure with respect to a certain k-local observable, some mean value of some k-local observable. If we say that the DAQC is weakly stable, if the mean value of this observable with respect to the difference of both states is independent of the system size. So it's just you can increase the number of qubits in the system, and this bound does not depend on that. And actually, what we obtain for the construction is that this distance only depends on the locality of the observable. The distance, this delta is the distance between the source Hamiltonian, so the characterized Hamiltonian that you thought, and the real one. And anything here depends on n. This is just depends on the plot, on the topology of the graph. But we went a step forward, and we are defining some strong stability based on definitions of Toby qubit. Essentially, we say that digital analog is strongly stable if the distance that you have, the norm between the Hamiltonian that you wish and the Hamiltonian that you are producing, that you are actually producing, is bounded by some function, some polynomial function of n. So it's only depends quadratically on the number of qubits. This is interesting because then this part here is how well your Hamiltonian is characterized. This means that if you want that your Hamiltonian, your final Hamiltonian is epsilon close, then the characterization of the original one has to be only quadratically good, not exponentially good. And what we obtain in our case is that this is quadratic. We also can extend into digital analog paradigm error mitigation techniques. And particularly, not only for removing or reducing errors related to decoherence and so on, but also related to the bank error. Remember that we are performing the single qubit gates on top of the analog dynamics, so this is introducing an error. As I said before, the idea is very simple. As I said before, if your single qubit gates were infinitely fast, there is no error. So what you do is to do the simulation for, it's just a zero noise extrapolation. It's very simple. What you do is to do the single qubit gates for different times. You find the fidelity or the mean value of some certain observable, and then you just extrapolate it to delta t, so the size of your single qubit gate to 0, and then it gives you the right value. Also, I'm not going to talk about this, but you can also mitigate characterizations errors. We have also developed techniques for this. And with this, until now, we have been talking, everything we have been talking about was essentially about simulations, quantum simulations, how to generate Hamiltonians. But the question is, can we use also this paradigm for already known quantum algorithms? Let's consider first the quantum Fourier transform, because it's very simple and very powerful. It's used essentially in most of quantum algorithms as a subroutine. And the idea that we will have is that this is the quantum circuit of the quantum Fourier transform, and the idea or the recipe that we will follow, the instructions that we will follow, are essentially to construct and to transform every control gate into CC gates, essentially. And when you have the CC gate, you can gather all of them because they commute, and you can construct essentially a Hamiltonian, set Hamiltonian. With this set Hamiltonian and single qubit gates, you can have a schedule for this Fourier transform. So as I said more in detail here, all the 2 qubit gates here can be gathered together as a structure like this one, that is a 2-body set Hamiltonian with certain certain couplings here that are these ones. And by using the rules that I showed you before, starting for any set Hamiltonian, you can construct these coupling terms. The idea is always the same. So let me repeat it. So you have your quantum circuit written in terms of control rotations and single qubit gates. You write these control rotations in terms of control set or set gates, and then these set gates, you gather them together, and you can write this as a Hamiltonian, a set Hamiltonian, and single qubit gates. Then you put everything together, and you have the digital analog, the bank digital analog construction. What we did here is to analyze the resilience of this construction with respect to different noises. These are the noises that I told you before, the control ones plus the environment ones, so the bit flip, measurement-based, measurement errors, and the coherence. And we apply the quantum Fourier transform to this family of states, which is a highly entangled one. Just we chose this one because it's interesting. And here we are analyzing the fidelity, the quantum fidelity, defined in this way, with respect to the beta parameter here. And we did it for different number of qubits. In the last paper, we have 4 more qubits, but it's not. I think this is enough to understand. In the case of 6 qubits here, what we observe is that are the green lines here. This is essentially the digital one. This one is the stepwise. So the stepwise works worse, as I told you before, because you have to switch on and switch off the whole block. And the larger the block, the worse it works. However, this is the bank. As you see, the bank digital analog works better than this one. Normally, this is because you are having a shorter algorithm, and you have also you avoid this control error. So the delta t to the third, the error introduced by the bank construction, is smaller than the error introduced by switching on and off in digital. You also see the same structure for 5 qubits here and for 3 qubits. Of course, the smaller the number of qubits, the higher is the fidelity. Of course, this is without any kind of mitigation techniques or anything. This is just direct behavior due to the different paradigm. We have used this for other kind of algorithms. Here, we started with the quantum Fourier transform. In this paper that was published recently, we had the phase estimation, and we have also did it for the HHL algorithm. I will tell you a little bit more now about this this case. This can also be used for variational quantum algorithms in which, instead of optimizing the local only the local gates, you have another parameter to work with, which is the times of the analog blocks. You can fix the number of blocks that you have, and you optimize also in T, which gives you, this is something that we are working on, but it's quite complicated. We are trying to prove that the expressivity of this is larger than the expressivity of a digital algorithm with the same depth. But we already applied this to the QAOA in this paper. We have also worked on implementations using the gross resonance effect in this paper with Oak Ridge. And in this one, we also use it for a specific construction, so from scratch construction in superconducting circuits. So let me give you some details about the HHL, because it's very interesting. The HHL, roughly speaking, can be divided into three parts. The first one is just the quantum phase estimation that I told you before. Then you have the ancillary qubit encoding here, and then is just the quantum phase estimation, the inverse of the quantum phase estimation. Essentially, this part, what does is to find the eigenvalues and eigenvectors of the matrix that you are trying to invert. This one is essentially codifying the inverse of the eigenvalues in an ancillary qubit, and this one just undo all the previous steps. Therefore, if you want to write explicitly this subroutine, what you have is a huge, exponentially large set of multi-control gates. If you want to decompose these multi-control gates into single qubit gates and control nodes, you can use the n-bit, n in the sense of the number of bits that you have here in the control, n-bit gray code, and you have some construction for this. If you decompose it and write it, as I said before, in the set gates and gather it together with the number of the set Hamiltonian, then you have the construction for this is stepwise, but in order to have the bank, you just have to put them together. And the good point of this one is it allowed us to find the optimal kind of topology that we need for a processor in order to implement this problem. And this is the kite-like construction, which is here essentially you have the logarithm of the size of the matrix that you want to invert, and here is the memory part that is related to the precision. And we have a patent about this topology with IQM. So with respect to impact, perspective, and conclusions of this, I mean, this is not exhaustive. There are new results, but these are the slides that I had already prepared, so I wanted to use them. There are results about superconducting circuits using this digital analog by Babukin et al. And what they did is to use this in IBM quantum computer, in the cloud quantum computers of IBM, and they found what the same that we saw. That is, they work pretty well. And there is the most impressive one is an experiment by the group of Yang Wei Pang, which was done with the 61 quantum processor, in which they implement a neural network using this digital analog, and they also found better performance. And there are also works about variational quantum algorithms using this DAQC, in which they use it for quantum chemistry to find the ground state of different molecules. And they also found that it works pretty well. But there are also other players working on this, like in the Pascal and other, that they are interested in this one, and IQM. Well, just to conclude, DAQC is a promising promising approach when you are dealing with niche devices. 2-qubit gates, in general, they are a source of significant errors and experimental noise, and they are accumulative in the depth of the algorithm, and this can jeopardize scalability. DAQC replaced this one by the natural interaction or the natural dynamics provided by your quantum platform, which is you are not trying to force the system to behave in the way that it doesn't want to. And this means that in general, this works much better. And also that somehow the algorithms that you are doing in this way, they are better optimized in the depth of the algorithm. This is not proven. This is an observation that we have done after working with this for a long time. And quantum algorithms can be expressed using this paradigm. And now, as I told you briefly, we are working on the effect of characterization errors in the source Hamiltonian, and see how this affects to the performance of the protocol. And we are also working now on extending this paradigm to qubits, not only to qubits. And with this one, I would like to thank you very much for your attention. If you have any question, please.
Thank you very much for your very wonderful talk. So now session is open for discussion and comments. So anybody have a comment on his talk? Okay. So may I ask a question? I have a couple of questions your talk. So firstly is that your digital analog quantum computation is a kind of the you want to replace the NISC to the digital analog quantum computer, right? And then so next step is that to try to replace the FTQC, right? Using the yes, digital analog quantum computation scheme. So my question is that actually that related to the quantum error correction. So in order to improve the error, of course, that not only the quantum error mitigation, but also you need to use the quantum error correction. So what kind of the quantum error correction is suitable for this digital analog quantum computer?
This is actually a very good question. This is one of the questions that I want to address in the future about if it's possible to do quantum error or how to adapt the quantum error correction codes to this kind of construction. And I have not an answer for this one, but I will say that well, in general, it's not so interesting, the digital analog, when you have full quantum error corrected protocol, because essentially the advantage, so if this is universal. If you don't care how long or how deep your algorithm is, then you are not. It's not so. It's like a kind of optimization to make it faster, but it's not a great advantage. Where we observe the highest advantage in this digital analog paradigm is precisely when you have noises. And this means, I mean, I don't know when we will have a fully error-corrected quantum computer. I think in a long time, probably. But yeah, it's the idea. But I think that the quantum error correction code will be possible to adapt this to digital analog.
I see. Okay, thank you. So, any question or comment? Yes, please.
Thanks for the talk. I just have a comment. So based on your construction for this digital analog computation, I think this is very much similar to dynamical decoupling in a sense, because there also you use these different sequences. In that case, the aim is different, that you try to remove the couplings because those are noises in that case. But here also sort of you modify the sequences so that you move away from a homogeneous coupling to the one that you want to simulate. So just wanted to point that out, and maybe there are deeper connections maybe to explore.
Actually, this is closer. I didn't say that, but this is closer, and we realized after we published the first paper on it. This is closer to NMR quantum computation, because what they did in the beginning, it was the goal. You have these NMR molecules, and then they have the Hamiltonian interaction that you have there, and they perform single-qubit gates in the molecules. This is closer to this one than to actually to dynamical decoupling, but it is true that it has some kind of flavor in the sense of quantum control approach.
Yeah, I mean, it's not very surprising, because I think even the concepts for dynamical decoupling were derived from NMR. So.
Yeah.
Good, interesting. Yes. Anyway, so any other question or comment from audience? Okay, I have another question. The experiment. Actually, you showed that your digital analog quantum computation scheme was already realized experimentally using several platforms, right? and you show some list, and which one is how can I get it? What kind of the platform is appropriate for this kind of the digital analog quantum computation? There are several choices: superconducting, ion, trap, and photonics, and also the other cold atom, and so on and so forth. So, what do you think about this? Which one is better for the digital analog quantum computer?
Yeah, this is a question that we also discussed many times, and essentially there is no one that is better than the other. The only what you need, so this can be adapted to essentially any platform, provided with one thing, that, as I said, you can perform single qubit gates much faster than the natural dynamics of the system.
Yes,
this is the only thing that you need. And you can, this can be adapted, for instance, to trap ions.
I see.
Actually, in trap ions is very similar, because the Mulmer-Sorensen gate is also a global interaction that you have there. It's a global interaction there, but you are applying this as a gate. So again, like for a fixed time. If you allow this to run for an arbitrary for free running times, this will be again digital analog in this sense. In superconducting circuits, it's already been done by different experimental groups and also different companies, and of course, cold atoms. The problem, cold atoms. Cold atoms. The problem that you have there essentially is the addressability, the single qubit addressability, because normally now the technology is going in this direction, and there are already some papers published on that with digital analog in cold atoms. But the problem until now is that you were not addressing one single qubit; you were addressing a bunch of them. So this was not very adequate for the construction. But I think it's not really, it's quite general, the approach.
Okay, good. So, question? No? So, if not, let's thanks to the speaker again.